let's check these out. Just kind of did these, like I called it before, like the bread and butter questions. Okay, these are fine, and they develop our intuition for Rolle's theorem, mean value theorem. Let's investigate a little bit further with this application. On a certain highway, a car passes one checkpoint at 11:17 a.m. and a second checkpoint at 11:45 a.m. So think like highway patrol's got these checkpoints set up. It's like this lone stretch of highway kind of out. It's kind of removed a little bit, maybe. Nobody's really patrolling it, but they have these checkpoints. Okay. The checkpoints are 41 miles apart. Could the driver be ticketed for speeding over the 65 mile per hour limit based just on this information? So we know when he passed through these two checkpoints, we know how far apart they are. Could he get a ticket for this? Okay, let's check it out. I tried to just summarize that information here. So he passed checkpoint 1 at 11:17. He passed checkpoint 2. It doesn't even mean he stopped. He could have just driven by it. Driven through, if you will. And those are 41 miles apart. Okay. Could he be ticketed for going over 65 miles an hour? And the idea is, would the patrol know that he must have gone over 65 miles an hour at least one time during that trip? So here's what we're going to do. We don't know the details of his journey. Maybe he or she was driving the same speed that whole 41 miles, right? Could be. Or it could have been that some parts they were driving slower, some parts they were driving faster. What we're going to do, we don't know any of that. What we're going to do is look at the driver's average speed. Okay. It's not too difficult. It's going to be how many miles were covered divided by how many hours it took. Total distance, total time. Well, what is that here? 41 miles. How many hours is this? Well, we've got it all in minutes, but okay, let's see. 45 minus 17. So if I just kind of do this maybe to the side here, 45 minus 17, it was 28 minutes. Okay. If we divide that by 60, I'm going to keep it just as a fraction. I got 7/15 hours. Just for now. We'll probably round it in the end. So let's see. How many miles per hour was this person averaging? Well, 41 miles over 7/15 of an hour. They were averaging 87 point, just a little below 87.9 miles per hour. Okay. Yeah, I think we can give them a ticket. So here's the thing. How is this connected to the mean value theorem, you might ask? Well, like when we do these calculations, doesn't seem like, how is this calculus, right? So we know their average speed. Well, but we don't know like how fast they were going at any given time. So they could have been driving this speed the entire 41 miles, right? But chances are some points they were going a little bit slower, some points they were going a little bit faster. Let me make a graph here and we'll see the mean value theorem in action. So we have miles that they traveled, and we've got hours here, miles per hour. All right. So let's say 11:17 was right there. And right there. And let's say 1145 was here. Okay, so we're going to say checkpoint 1, right? Let's say that was 0 miles. Now, as far as our count goes. And 1145, right? Now they're 41 miles down the road. So maybe the line connecting them is just a straight line. A straight line would mean they were driving exactly that average the entire way. But more likely, you know, at some points they were going a little bit faster and some points slower. And so it might look something like that. So if we know, break out my ruler here, my straight edge. If we know the average, right, which is what we did in that calculation just above, if we know the slope right here is 87.9, then at some point, at least one time, the slope of the tangent line must have been the same. And it looks like the way I drew it, it happens twice. So, you know, kind of this graph is how far they've made it, you know, down the road, like in the miles. So looks like they were really booking it right there. They were driving well over 90, maybe even over 100 right here. Okay. And they kind of started to slow down. And at this moment, they were going to 87.9. They kept slowing down. And for a little while, they were hardly making any progress down the road. They almost came to a complete stop. And then they just kind of sat there or like drove really slow for a little while. Maybe it was the nature of the road, made them slow, I don't know. Maybe they just stopped on the side for whatever reason. And then they got back on the road and picked up speed again. And at this moment, again, they're driving at 87.9 miles an hour, and they're still accelerating, going even faster as they come through that second checkpoint. So yes, we can definitely, the patrol can definitely give them a ticket for breaking the 65 mile an hour limit, because we would know at least one time they were going 87.9, and more likely, you know, if their speed did vary, then at other points they were going even faster than that. Okay. So kind of a simple problem, right? No calculus there, but yet has a calculus, you know, explanation if you look deeper. We've got one more example, something you might see. This actually goes back to Rolle's theorem. For f of x equals tangent x, is there a value of c on 0 pi that satisfies Rolle's theorem? If so, find it. If not, explain why not. Okay. So I think I need a new piece of paper. So we're looking at f of x equals tan x. Is there a c on 0 pi that satisfies Rolle's theorem? If so, find it. If not, explain why not. So some people just jump like headlong into finding the value of c with the derivative. Remember Rolle's theorem, that's when f prime c was equal to 0. But you don't want to do that. You want to check, you got to check hypotheses. If those are not satisfied, then all bets are off. Is f of x continuous on 0 pi? You would think, well, what's the big deal, right? It's just tangent. Turns out there is something that goes wrong with tangent between 0 and pi. There's a vertical asymptote at pi over 2. Let's call it at x equals pi over 2. So because of that vertical asymptote, it's not continuous. And so we cannot guarantee the conclusion of Rolle's theorem. So just something to look out for, be careful about. A C value. Here's like our answer and our explanation. Satisfying Rolle's, we'll say, need not exist. Now we're not saying it doesn't, it still could, but we're just saying Rolle's theorem at this point doesn't apply here, and so there's no guarantee. Need not exist because f of x equals tan x is not continuous on the interval. Or you might even say, a little bit simpler, interval, that the three hypotheses of Rolle's theorem were not satisfied. If you missed this and you kept going, and you took the derivative and you're like, okay, I know the derivative of tangent, right? You could even plug in, right, Rolle's theorem. We know that the y values of the endpoints have to be equal. That would be true here, right? The tangent of 0 is 0. And for f of pi, the tangent of pi, if you check that out, is also 0, right? It might seem like all things are good, but if you then set the derivative equal to 0, the conclusion of Rolle's theorem, you're not going to get very far with that. You might think, okay, well, secant squared x equals 0. I'll make this 1 over cosine squared x. That's not going to get you very far. There's no solution here, right? If you were to multiply cosine squared over here, you'd get multiplied by 0, 1 equals 0. Wouldn't make any sense. There's no value of x that will satisfy that. And the reason, of course, is because we never satisfied the hypotheses in the first place. So there may be some questions like this to really test your understanding. All right, you guys. That is it for this section.